Hey, this is Leach with Simpson Math, and in this video, we will continue our discussion about graphing transformations. We'll pick up where we left off. In the previous video, we discussed these notes. We discovered all these different transformations, the shifts, the dilations, the stretches, the reflections, all those on Desmos, and we wrote down these notes. So make sure you have these written down. I'd even have them written down on a separate piece of paper so you can refer to them as we go through several examples where we will be transforming the 7 parent functions that we know so far. So let's get started. All right, so for the examples we're going to be looking at today, we're going to do 5 things. We're going to identify the parent function by name and equation, and then we'll state whether the extra number that's in the equation, whether that's an A, a B, a C, or a D, and then we will we'll describe in words what's happening, and then we'll graph it, and then we'll also state the domain and range for practice, and we'll do it in both notations, again, for practice. So let's take a look at g of x, which is the square root of x minus 4. So looking at this, what is the parent function that we can see is associated with this is the square root of x. This minus 4 is a number, so this part right here, the square root of x, is the parent function. So I can make that note that the square root is our parent function. All right, so then this minus 4. So if you recall from our formula, the formula is right above my head, we have the a, the b, the c, the d. The a, the b, they're multipliers. The c and the d, they're adding. So that means the a and the b multipliers, that's the dilations, that's the stretches. The c and the d, those are the shifts. The b and the c, those are inside, that's affecting things horizontally. And the a and the d, they are outside. So looking at this, I can see that this minus 4 is adding on the outside of the function. So that means it must be the d. And so our d is negative 4. So now in words, what's happening? So if we go back up and look at the notes that I have right here, if d is negative, if it's a minus d, we're going to go down d units. So or down the absolute value of d units. So we're going to go down d units. So let's graph this. In a dream world, I could be a psychic and I could see into your brain as you see the parent function, that square root of x function, and then when you just pop down 4, and it's like, oh, I see it in your brain, great. And really, I feel that I have achieved success if you can see these transformations in your head. So by the end of this video, that's my goal, is that you should be able to see these in your head. But we got to put them on paper. So I'm going to just plot out the parent function dots. We should have these memorized at this point, 0, 0, 1, 1, 4, 2, 9, 3. And then I'm just going to move them down 4. So the 0, 0 dot moves down 4. So down 1, 2, 3, 4. And right there, I'm going to put a dot. I'm going to do the same thing to the 1, 1 dot, move it down 4. Same thing to the 4, 2 dot, move it down 4. Same thing to the 9, 3 dot, move it down 4. So I've moved all my points down 4 units. That's it. Swoop my square root graph. And there we have it. I just graphed g of x, which is the square root of x minus 4. For good measure, it's also good to label that is g of x, just in case we have multiple graphs at some point. Especially if you do go ahead and complete this. Oops, let me turn that orange. If you do want to graph this, or you see that looks like the square root graph, and you have multiple graphs, then definitely do label this. So you can just label this as square root of x, because we don't have it defined as f of x. But you could use f of x and then whatever that is. So if you have multiple graphs, make sure to label. All right, so now let's do the domain and range. So domain is my set of x's, and if I'm doing interval notation, I'm going to see as far left as I can go. Well, there's nothing over here, so as far left as I can go is actually right here. And make sure you're looking at the x-axis when you're pulling your number. So again, think of an industrial press that's just compressing everything onto the x-axis here. And so I'm looking at from 0 to infinity for my domain. And then my range, how far down can I go? What's the lowest And again, I think of bookends, just bookend smashing it onto the y-axis. So this gets smashed onto the y-axis, and then we're at -4. That's as far down as I can go. And then how far up can I go? Well, to infinity. So here's my domain. I just described that in interval notation, but you can also do that in set notation, which is the set of x's such that x is greater than or equal to 0, or y's that are greater than or equal to the -4. All right, so let's graph h of x is equal to x cubed plus 1. So first, what is that parent function? Yep, that's the x cubed. That 1 isn't a part of the parent function, but that x cubed tells us it's the x cubed, so it's the cubic parent function. And then that plus 1, what letter is that? Is that A, B, C, or D? Yep, again, we're adding on the outside of the function, so it's the D. And then if D is 1, you go back and you look at your notes, and you see that I am going to be, if it's an add 1, if D is a positive, I'm going to be moving my function up 1 unit. So it's going to be a shift up 1. So let's plot my parent function dots. So 0, 0, 1, 1, 2, 8, and then -1, -1, -2, -8. All right. I'm not wanting to swoop it and graph that just because it sort of kind of make my graph be a little bit messy. So now I'm going to shift all those dots up 1. So just if you see a dot, move it up 1. Move it up 1, up 1, up 1, up 1, and up 1. All right, let's swoop it. So I'm starting at the bottom, a little bit too far over. Start at the bottom, go through the, not that kind of a wiggle, goodness. Swoops through the dot right here. It's pretty quick switch through. And then kind of ish, more smooth and straight up. And don't forget our arrows. Now it never ever goes vertical because this does keep going forever and ever and ever and ever and ever out. So our domain and range here is all real numbers or from -infinity to infinity. So we just took our cubic function and we just popped it up 1 unit. Our next example is b of x is equal to the absolute value of x plus 5. So again, what's our parent function? Well, it's the absolute value. That's the kind of math that's happening to this function. So it's that absolute value. And then what's that plus 5? Well, we are adding again, but that plus 5 is inside the function. So it's inside the function. It's inside those absolute value bars. So that is going to be our c. Now, when it comes to c, some people will define the c in and of itself as negative, or that subtraction is just kind of hanging out there. So it's weird things are happening with that sign. So when I label c, I always just say c colon, and then I just write the binomial that's with the x, and so that's x plus 5. I'm just doing that for myself because there's a little bit of weirdness as to whether you define that negative as a part of the c or that negative is just a part of the formula and not the c. So to clear all confusion, I would just write that binomial that it's that x plus 5. So then if I see an x plus 5 that's associated with that c, what do I need to do? Well, let's go back up and look at our notes. So pull out your notes, and you see that if it's a plus c, then we're going to be going to the left that many units. So I'll actually swooped up there. So if I see this x plus c, and again I wrote it as that binomial, I will be going left. Again, that feels backwards, but we talked about that in the last video. Left absolute value of c units. So ignore the signs when we were talking about the number of units. So we're going to be going left 5 units. So then let's graph this. So I'm going to graph my parent function dots. I start 0, 0, 1, 1, 2, 2. Might as well do the 3, 3. And I could keep going a little bit further, but I think that's good. I might do just go up to 8, 8. That's what I have on my graph. I do want your graphs to go up to 10, 10 if possible. Negative 10 to positive 10. All right, so there's our absolute value, and we're going to move it left 5. So take every dot and move it left 5. So I'm going to go left 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You should see that at this point I'm not having to count anymore because I can rely upon the pattern of dots once I placed one. And move over that one. There we go. And so some people, and this is a little bit of a sneak preview of my next set of videos where I'm going to be talking about multiple transformations. Or right now we're just doing one change, one stretch, one reflection, one shift. But if we're doing multiple things, you see generally what I like to do is I like to almost move a key point, often something that's associated with this origin, because if I just move this over, that origin point over, then it'd be really easy for me to graph. I could then basically almost graph my parent function. So just a little bit of a sneak preview and a little bit of a tip that you can use. So move a key point, and then you can just follow that pattern. All right, so now that I have my dots done, let's swoop it. So straight lines as best as possible without a ruler. There we go. And this way. And I would like, missed a little bit, I would like for you to make sure to go to the end of the graph. Please don't make a teeny little baby short absolute value. I want to all the way to the end of your grid, and then don't forget about the arrows. All right, so let's do our domain and range. So again, how far, for my domain, how far left can I go? Well, all the way to negative infinity. How far to the right? Positive infinity. How far down can I go? Well, the lowest point is this point. That point is -5, 0. What's the y component of that? That's 0. Or again, bookend it and smash everything onto the y-axis. You'll see that the lowest point is 0 all the way up to infinity. So there we go, negative infinity to infinity, or all real numbers for the x's, and square bracket 0 to infinity, or y is greater than or equal to 0. All right, let's take a look at t of x, which is 1 over x minus 3. So first up, what's our parent function with this? Well, our x is in the denominator of a fraction, so that must mean that it's the rational parent function, 1 over x. And then that minus 3, is that minus 3 adding or multiplying? Well, it's adding, or I'm adding a -3. All right. And then, is it inside or outside the function? Well, it's inside the function because, well, what's in the function right now? That's in the denominator. Where's the -3? In the denominator. So that -3 is our c, or x minus 3. So we have a negative c, you can think of it like that, or subtraction. So then if it's a -3 for my c, I'm going to be going to the right 3. So we're going to the right 3 units. At this point, you're still kind of learning and getting familiar with this. If you don't have this memorized, which I don't expect you to have it memorized right now, have those notes handy. Over the years when I've taught this, I ask students these questions and they go, I'm like, no, this isn't a guessing game. This is an identification. You've been seeing the process of which I've been going through to identify. Is it inside or outside? Is it adding or multiplying? And then once you identify it, you look at the notes and you state it. There's only one option. So it's x. If it's an x minus c, it's right c units. End of story. All right, so now let's graph the 1 over x. So my parent function dots are the half 2. Yes, you do. Oh, let me make my pen bigger. Half 2, 1, 1, 2 half. And then on the other side, we have the negative half 2, -1, -1, -2 halves. Now, I do have absolute value, misspoke, the asymptotes right there. But I'm not going to graph those because my parent function ones, I need to move it. So I want to move it first and then formally draw my asymptotes. So this is going to the right 3 units. So I'm going to take every dot and move it right 3. So you go right 3, 1, 2, 3. So it's again going to be on a half. That's fine. Then 1, 2, 3, 1, 2, 3. And again, once you get the 1 point moved over, then the others should be in that same relationship. So move over this -2, 1, 2, 3. So right here. And then the others should be in that same relationship when I move them over. Oops, too far. There we go. Okay, so I moved them all over. Now let's draw the asymptotes. So I just slid it over to the right 3 units. So my horizontal asymptote, if I have a horizontal line and I just slide it over, that horizontal line doesn't change. So I still have a horizontal asymptote at y equals 0, and let's label that HA is y equals 0. But if I have a vertical line and I move it over 3 units, notice it does change. So it moves from being x equals 0 to x equals 3. So let me draw that dotted line. So I have a vertical asymptote, a VA, at x equals 3. And again, with the vertical horizontal line, just think what axis is it crossing over here. X is equal to 3 right here, and that's the same up and down. And then similarly horizontally with the y. All right, so now that I have my asymptotes drawn and I've gone blurry, let me fix that camera. All right, so now let's swoop our points. So I'm going to start over here on the coming from the right-hand side, and as close as I can to the asymptote, gradually moving off, swooping through the dots, and then writing up the other asymptote, getting closer and closer to it, and then on the other side as well. So I'm going to come from this left side, practically on top of the asymptote, gradually getting off of it, swooping through the dots, and then closer, and arrows all around. All right, so just again, a few tips, a few reminders about the rational parent function. Make sure that we don't, when we start going up, do that and move away from the asymptotes. That's really easy because you should start arcing with your hand instead of going up. Don't start pivoting on your wrist. It's just easier for students to get in a hurry and do that. It's a very big no-no because we're gradually getting closer. Also, students will sometimes hit this last dot and then just go straight up, or they're afraid to get close to the asymptote. Don't be afraid to make it appear as if you're touching your asymptote. That's okay, because we talked about that in our parent function video. Our pins have thickness. Just get as close as you can, gradually, and then we'll hit a point that it might look like you're touching, but that's okay. Just make it a gradual approach. All right, so now let's do the domain and range. So for the domain and range, we can just basically think about that if these asymptotes weren't present, it would be all real numbers. So for set notation, you just say what number isn't allowed, and then you're good to go. So for my domain, it's everything just except at 3. So everything but 3. So x can't equal 3. So then for interval notation, I'm coming from negative infinity all the way up, getting closer to 3. So it's a parenthesis right before 3, that union, which is a piece of glue. Then we hop over to the other side of 3 and move on. So here's my domain and range. So like I said, negative infinity to 3, union 3 to infinity. And then do have this note for set notation. Formally, it's the set of x's such that x is a real number, but x is not 3. There's an understood real number here, or understood statement that we're dealing with real numbers. So we can just say that x can't be 3, and that will be fine for us. And then for our range, it's very similar. Negative infinity to 0, 0 to infinity. That union is a piece of glue that holds it together. And then x or y can't be 0. Now, before I move off of these shifts, I want to just show you what it would look like on these equations if instead of it being a C, if it was a D, or D, it was a C. So here, this was a C. What would this minus 3 look like if it was a D? It would be 1 over x, and then a minus 3 just outside of the function. So that would be a minus 3 that would move the function down 3 units. With this absolute value, it would be the absolute value of x, close absolute value, and then plus 5. So here, that plus 5 would be a D, and we would go up 5 units. For this cubic, it's going to be open parentheses, x plus 1, close parentheses, cubed. So here that plus 1 is inside the function, but adding inside the function. And so here we would end up going left 1 unit. And lastly, for this square root of x minus 4, it would be a big square root of x minus 4, with that minus 4 being inside the square root. So here that minus 4 would move the square root function to the right 4 units. All right, let's take a look at f of x is 2x squared. So first up, what is the parent function? It's the x squared, it's a quadratic. So it's our quadratic x squared. And then what's our letter? Now just to be clear, this 2 is not an a, b, a c, or d. This 2, you can think of it like the last name of the parent function. It defines its family. So that is a part of what is defining it being a quadratic. That is not a part of the a, the b, the c, or the d. So then this 2 here is our a. And it's an a because it is multiplying on the outside. So we are multiplying on the outside. It is our a. And look in your notes, when it's a is bigger than 1, it's a vertical stretch by factor of 2. So we can say just that, vertical stretch by factor of 2. So let's plot our parent function dots. I do have the table defined right beside us. For some students, especially when we start this dilation process, it's going to be handy to be able to see the table of dots. Others, just having the dots graph themselves is fine. You'll reach a point that you won't even need to graph the dots anymore. You'll just have it in your brain. So let's doing a vertical stretch by factor of 2. So if it's a vertical stretch, what variable is changing? Are my x's changing or are my y's changing? Well, it's my y's that are changing. So if I'm taking every y value and doubling it, that would make a vertical stretch. So you can literally look at this column of y values and just double them. 0 times 2 is 0, 1 times 2 is 2, 4 times 2 is 8, 9 times 2 is 18, so forth. And then you could just graph 0, 0, 1, 2, 2, 8, 3, 18, and that's it. That's what we need to do. And then, of course, their negative counterparts. What I often do is I'm more of a visual person. So I just like looking at these dots over here and go, okay, well, if I have 0, 0, and I double it, and I double the y's, well, I'm still just going to be at 0. All right, what is this y value? What is its height right there? Well, it's 1. Double it, we're now at 2. If I'm at what is this point's y value? Well, its y value is 4. Double it, now it's at 8. What's this point's y value? Well, it's 9. Double it, we'd have 18, which I don't have room to graph it. But I need to be mindful that the next dot is 18, so that way when I swoop these dots, I don't do this, okay? Or straight up, or swoop over back towards the inside, making it no longer be a function. All right, I can do the other side. 1 doubled is 2, 4 doubled is 8, and again 9 doubled is 18. With the parabola, with the quadratic, you can take advantage of that symmetry, and you can draw it that way. All right, so now I can just swoop it. So I'm going to draw my parabola, coming up from up here. I'm mindful that I'm coming from as if this way up there was 3, negative 3, comma 18. So I'm kind of coming from that direction, moving on down, going to that point, nice flat curvy bottom. Oops. I think they have an undo option. There we go. And arrows. Again, mindful that it's going to 3, 18, or negative 3, positive 18. All right, so there's my parabola. Let's do domain and range. So what's my domain? Well, parabolas are going to go left forever and ever and ever, and right forever and ever and ever. So it's going to be negative infinity to infinity, or all real numbers. But then my range, it's going to go all the way down to 0, and then all the way up. So this didn't change the parent function. Sorry, this didn't change the domain and range from the parent function, just because it was stretched, and just the nature of this particular example. So it's a bit of a coincidence, but there's some meaning behind it. All right, let's move on. All right, let's talk about h of x is 3 over x. So what parent function is this? Well, we have an x that's in the denominator of a fraction. So that must be, again, our rational function, 1 over x. Right? And so we have a 3 that is multiplying. And was it multiplying inside the function or outside the function? Well, inside the function would be in the denominator. So that's not in the denominator, so that's in the numerator. So that's an a of 3. When it's an a of 3, what's going to happen? Well, it's a vertical stretch by factor of 3. So let's say just that. Vertical stretch by factor of 3. Okay, let's graph our parent function. So half 2, yes you do, 1, 1, 2 half, and then the negative counterparts. All right, so there's our parent function. I'm going to go ahead and graph our asymptotes because if I stretch things vertically, the asymptotes are not going to change. So let me go ahead and get those graphed on here and labeled. Now I'm going to go ahead and follow our rules of just multiplying our y values times 3, but I'll give you a little bit of a spoiler. By multiplying on my y values by 3 that are from my parent function dots, I'm not going to get enough of a picture to probably accurately graph this. And there's actually a really interesting pattern when it comes to stretching rational functions. That's why I chose to make sure to talk about this one. So I'm going to go ahead and do our process of multiplying everything times 3. I'm going to do it in a lighter blue because I actually have an easier way to stretch rational parent functions. So let's quickly do our dots just for practice. So this first dot is half 2. So if I multiply the y value of 2 by 3, we're at half 6. So like I said, putting that in a lighter blue. Then this is a 1, 1. So 1 times 3 is 3. So I'm going to put a dot at 1, 3. And then this 2 half, if I multiply half times 3, I'm at 1.5. So notice we're going to worry about this first quadrant right here. Notice that if I was like, okay, now we have our dots, swoop it, you could be like, do you have a really nice set of dots right here? But I don't have much guidance over there. Like, yes, it's going to be gradually getting closer and closer and closer to the gradually closer to the asymptote, but how quickly? So there's there's a pretty decent distance here. And what if this was a 5 or a 10 or something? We need a little bit more help. So we can be mindful of a few more parent function dots. So if I was at 3 specifically, so if I was at 3, this would be up at a third. I would go up a third for my dot. And what would happen if I multiply 1/3 times 3? Well, I would be at 1. And so there's going to be an interesting relationship between the values that have a in it. So what I do, this is what I can do whenever we're stretching the rational parent function, is at minimum, instead of graphing the half 2, 1, 1, 2 halves and just moving those up or down, what I encourage you to graph is the point 1 comma a and a comma 1. So that's meaning to graph the point 1, and what's our a? 3. So 1, 3, and 3, 1. Mathematically, those points work because remember, this is the reciprocal, or another name for the rational parent function is the reciprocal function. So if I multiply 1, so if I'm at this 1 point right here, at 1, and I multiply it times the a, it will always give me a, because 1 times a is a. But then remember, it's the rational, or nickname for it is the reciprocal parent function. So when I find if I plug in an x, if I plug in 3 into 1 over x, I'm going to get 1 over 3. So if I was to multiply, what number can I multiply by 3? Sorry, what number can I multiply by 1/3 to get 1? Well, that's 3. That's going to be this reciprocal. So if I'm plugging in when x is 3, that's evaluating the function at 1/3, multiply it times my a, which is its reciprocal, I'm always going to end up at 1. So 1 comma a comma 1 every time. Now, you're more than welcome to then do a few more dots, because if it was 1 comma 10 and 10 comma 1, you'd be having dots way up here and way over here. Wouldn't it be a bad idea to take a fifth, multiply it times 10, and move that up to where it belongs, to put in a few more dots to just evaluate to fill that in. But at minimum, 1 comma a comma 1. And then same thing on this negative side. Negative 1a, negative a, negative a, negative 1. Another way to think of this is you can also almost think about taking this 1, this negative dot, and splitting it into two different directions. So negative 1, negative 3, negative 3, negative 1. So those are the points that I, at minimum, are going to want you to graph. Notice it doesn't get as quickly, run to the asymptotes, but it still gradually moves closer and closer to them. And I have my arrows. So if you just graph 1 comma a comma 1 will be good. Now, an interesting fact about this particular function is when you stretch it vertically, it stays symmetric, as if we are also stretching it horizontally. It's like if you're zooming in on an image in Word or something, you hold the Shift key, or Word is forcing it to stay in proportion. It stretches proportionally. So if I stretch it vertically, it goes, no, actually I want to do it both ways. So actually it kind of does it both ways. And here's why. Mathematically, these two things equal each other. If I had a 3 over x, that mathematically is the same thing as a times a 1/3 in the denominator. And if I asked you to identify that letter, that would be a b. It would be a b of 1/3. As we saw, if we see in our notes, if I see a b that is less than 1, if its b is less than 1, it's going to be a horizontal stretch by a factor of its reciprocal. So this is a horizontal stretch by a factor of 1/3. It is literally both. Horizontal stretch by a factor of 1/3, sorry, horizontal stretch by a factor of 3, and vertical stretch by a factor of 3 at the same time from this same number. So it is quite literally both. It moves it symmetrical. All right, our domain and range stays at our parent function values because we didn't actually do any shifting or reflecting. All right, let's take a look at h of x, which is 4 times the square root of x. I would like you to pause the video and try this one on your own. All right, welcome back. Let's see how you did. Well, this is the square root function. A is 4, which means it's a vertical stretch by a factor of 4. I have my parent function dots right here, so I'm going to multiply all their y values times 4. Well, if I multiply 0 times 4, I'm still at 0. 1 times 4 is 4. 2 times 4 is 8. And 3 times 4 is all the way up here at 12. So let's swoop this. And there's the square root function, or there's a function for square root of x. All right, so now we have k of x is equal to the cube root of 2x. Now, first up, well, what's the parent function? It's the cubed root. Cool. But what is that 2? Now that 2 is multiplying on the inside of the function. Since it's multiplying on the inside of the function, that is the b. b is 2. As we see in our notes, if b is 2, this is a horizontal shrink by factor of, flip it, 1/2. This is a horizontal shrink by factor of 1/2. So let's graph our parent function dots and see if we can shrink this horizontally by 1/2. So 0, 0, 1, 1, 8, 2, negative 1, negative 1, negative 8, negative 2. So this is a compression in. It's like you're taking an accordion and squeezing everything in by 1/2. So just like we did before, where we took our y values and doubled or half, now we're taking our x values and halving. So I literally could just take this be a negative 4, negative 1/2, 0, 1/2, 4 if I just half all those numbers. So let me write those again. -4, -half, 0, half, and 4. Disregard this x completely, and then graph -4, -2, -half, -1, 0, 0, half 1, and 4 halves, and we're good to go. Visually, over here, I can, with my parent function dots already kind of dotted and graphed, I'm going to do that same thing. So I like to start at 0, 0. If I half the x value of 0, still 0. Half the x value of 1, so I'm talking about this x value of 1, and I'm going to half it and put it there at that x. So half it, and I'll be at half 1. Then I'm going to look at this x value of 8. I'm going to half it and put it right there at 4, 2 instead of 8, 2. We could be mindful of where the next one would be. The next one would be, next out would be 27, 3. So if I half 27, that is 13 and a half. So not quite here, but not too far. So actually it would be like right about here. All right. So then let's move on. So again, let's half the -1, and we'll be at -half. Half the -8, and we'll be at -4. So now that I've shrunk it horizontally, I can swoop this. Oops, missed. It's a little bit squattier. I was going a little bit too steep. A little bit smoother if possible. This is ugly. Try all this again. Let me just start from the middle. That's sometimes easier. A little bit of a S kind of curve there. There we go. There we go. That's better. All right. So there is our cube root function that's been squeezed in by a half. And then nothing's changed about our domain and range. -infinity to infinity are all real numbers for both the domain and the range. All right, so what about a of x, which is negative times absolute value of x? So that negative is multiplying, or you can think of this as a -1, multiplying on the outside of the function. So that's our a, and the parent function is the absolute value of x. And if I have a negative a, then it's a reflection over the x-axis. So let's graph my parent function dots. And go ahead and also do the 8, 8, -8, -8, because that's the edges of my grid. Again, I would like yours to go to 10. All right, and then it's just going to reflect it over the x-axis. Or you can think quite simply, remember that a's are multiplying the y values. So if I multiply all y values times -1, if it's a positive, it's now negative. And if we had some that were negative, it would then swoop up to be positive. So that's why it does this reflection over the x-axis. So reflect this point down. If I reflect 0, 0, still at 0, 0. Instead of going up 1, I'm now down 1. Instead of up 2, I'm now down 2. All my y's just literally get negated. You can think of it, again, it's either a reflection or all my y's just are negative. Instead of going up, you go down. Instead of down, you go up. All right, there we go. So now really important here, I want you to, if you haven't done it yet, go ahead and pause the video and do the domain and range. All right, so notice that the domain is the same. All real numbers are -infinity to infinity. But then our range, it's not the same. Before it was 0 to infinity or greater than or equal to 0. Now, my lowest value is -infinity and my highest value is 0. So make sure you always do smallest to biggest. This is the biggest time when students will do biggest to smallest. The smallest is -infinity. The biggest is 0. So 0 to -infinity to 0. Or make sure we have less than or equal to 0 for the set notation. All right, last one for us to work out. F of x is the square root of -x. Now we did look at this one in the previous video. This is a square root function. that -1 is a b. So this is a reflection over the y-axis. So again, let me just quickly graph it. So 0, 0, bigger point, 0, 0, 1, 1, 4, 2, 9, 3. And then if I, here I'm multiplying all of my x's times the -1. So they just get negated or just reflect over the y. So 0, 0 is still there. Then reflected over the y-axis, reflected over the y-axis. Instead of going to right, I'll go left. Instead of left, I'll go right. And there we have it. Let's swoop this square root. A little bumpy. Let me try that again. It's a bit better. Okay. So there we have this. Now, very important. I want you, if you haven't done it yet, pause the video and do the domain and range. All right, so this time the range is the same. I didn't change the range. I just changed the x values, not the y values. So the range is still from 0 to infinity. That bothers some students, but again, bookend it. Smash this onto the y-axis. I have my lowest value dot is 0, and I'm going to have dots forever and ever and ever up to infinity still. So this is not a change to my range. What does change is the domain. So if I have it's now going from all the way from negative infinity all the way up to and stopping at 0. So square bracket at 0, or x is less than or equal to 0 for the set notation. So make sure we don't get tripped up about the domain or the range on this one. I want you to notice that notice whenever I switched I reflected over reflected over the x-axis, and my y's changed. Appropriately, the range changed, but not the domain. When I multiplied my x's times the negative and reflected over the y-axis, appropriately, the domain changed, but not the range. So that's a nice little relationship there. One more thing that I want to point out about a's and b's, I think they're all were obvious except for this one. If this 2x squared was a b, make sure that we're clear, it would be 2x with parentheses squared. So that would be the b, this is the b, whereas this is the a. Those parentheses are key and do matter. All right, I'm not going to go over these in too much detail, but just some quick fire examples. So if I have an x plus 5, which is a c, you don't have to graph all the dots, just all the parent function dots. If you see, oh, that's going to be the absolute value, move it left 5 units. You can even think that I'd be moving this origin point left 5 units. I'd be here and then graph the absolute value. It's good to go. So that's kind of my tip, is move the shift left 5 and then just graph the parent function starting at -5, 0. All right, for it to be easy here of this 1 over x minus 3. So this is the example of that minus 3 that's on the outside. Just move the origin, just shift down 3 like this, and even graph my asymptotes. And then if you just graph the parent function around that 0, -3, so from here, half to 1, 1 to half, that's going to make that be a little bit faster. And then lastly, here's just another little bit more detailed example about when a is 2, about how we do that double. So there's just a few more examples. And as always, remember, you can play around with Desmos. So if you're thinking, I think, did I do this right? Put it into Desmos. If it looks right, if it looks what you see on the paper, like on the problem, and what you see in Desmos, then what you see is what you get. So hopefully this helps you understand the graphical transformation a little bit better. And the next series of videos about graphing are going to be where we're going to be doing not just one change, but multiple changes to the same graph. So I'll see you in that next set of videos.